Welcome to the course Business Analytics and Data Mining Modeling using R. So in the previous lectures we have been discussing classification and regression trees, and specifically we were talking about the classification trees. We talked about the recursive partitioning. We did few exercises. We talked about the impurity matrix as well. So we were doing exercise related to that. So the Sedan-Carr data set that we were using, and we talked about the first partition, the hypothetical partition that we created, and we also computed the Gini index values and entropy values for the original partition and then after first split. Right, so then we also computed the impurity values. Then we also compared whether there is any reduction in impurity or not. So let's continue that same exercise. Now we'll do second split, and then again further we'll move to applying classification and regression tree. So this was the particular graphic for scatter plot for household area versus annual income, and this was the first split we created. And as we discussed, the upper rectangular and lower rectangular being symmetric, we computed impurity metric values as well. So similarly, second split can also be done. The second split can be done at this point. So you can see this particular value 0 and 18.8 at annual income value of 7, and up to this 18.8 of household area value. We can create this separator, and again we will have these two rectangular partitions. Here now you can see this particular partition is purely homogeneous, because we have all the observation, that is 2 here belonging to the same class, that is owner. In this particular partition we will have 3 and 1, 7 observations belonging to the non-owner class and just 1 observation belonging to the owner class. So the reduction in impurity can be clearly seen, and here this has already become homogeneous. So in this fashion we can keep on creating partition, and that is also to explain you the typical process that happens in classification and regression trees. So what could be our second partition? So third partition. So this could be another line. You can see this particular after this partition we'll have another area with homogeneous area, all the observations belonging to the same class, and this one will have just 1 observation belonging to the other class, right? So in this fashion we can keep on continue our partitioning process till we create till we reach or create all the reach the partitions which are purely homogeneous. So now you can see that any partition that you see, it is pure homogeneous partition. The observations belong to the same class, right? So this is now all the observations have been correctly classified. So the performance of this particular classifier is going to be 100%, all the observations correctly classified. But of course there is overfitting that has happened. So how do we adjust, how do we get rid of this overfitting in our model? This we'll discuss in coming lectures. So let's continue with our exercise of based on Sedan-Carr data set. So let's look at the structure of the data frame that we have. So this is the Sedan-Carr data set that we have been using, right? Annual income, household area, ownership. Now to apply a classification and regression model, specifically classification model in this case, we need to have this package installed in our R environment. So rpart is the name of the package for cart procedure. So we are going to load this particular library. So in this particular package, the function that we use for modeling is rpart, and there we have a particular argument method. So in this method we have to assign value as class for classification tree and ANOVA for regression tree. Since we are doing classification task right now, So what we will do, as we have been doing modeling in previous other techniques, so mod R part, our outcome variable here is ownership, and remaining variables, it is going to be built on remaining predictor other variables that are predictor variables, 2 of them, annual income, household area. Method is class because we want to do a classification. Data is df. So all the observation we are going to absorb in this modeling process. So this is mainly for demonstration of classification tree. So we will absorb all the observations in this process. Then another argument that we have is control. So this control can be used to call another function rpart.control to set few more parameters. To understand more about these functions, so first let's type rpart in the help section, and you would see that the package name is rpart here, the function is rpart, and let's look at some of the arguments here. So formula, this we have already specified, data, weights, subset, and other variables. You can see control is the another one more argument, and parameters, parms, that is one more argument. Some of these we are going to use. So let's focus on the control argument. So let's scroll down. So this control is essentially a list of options that control details of rpart algorithm. So what could be the list of options that we will have to check from this function rpart.control. As you can see in the code itself, we are calling rpart.control function, and within this function we are passing on the arguments. So let's look at the definition of rpart.control. So this is the function. So various parameters and control aspects of rpart. So you can see there is one first argument is min split. So minimum number of observation that must exist in a node in order for a split to be attempted. So you can see the default values is 20. However, we have specified as 2. So even if 2 observations are there, we would like to go for the split. Essentially, we are trying to simulate the scenario of a full grown tree. So for that purpose we are doing this. So minimum split, we have specified the value as 2. So if there are 2 observations, we would like to split to be attempted. Now the next argument is min bucket. So here you can see minimum number of observation in any terminal node. So here you can see min bucket, we have specified 1. So right, so minimum number of observation could be 1 as per our specification. The default value is this based on this computation, round of min split divided by 3. So min split value it would be divided by 3, and then round would be taken. So that is the min bucket value, default min bucket value. But as we said, we want to simulate the full grown tree process. So therefore min bucket has also been kept at a very low value of 1. Max complete, number of completed splits retained in the output. So this is 0 because we are not interested in other completed splits. We are just interested in the best, the optimal split combination, predictor value combinations. So that this has been specified as 0. You can see max surrogate, the surrogate split. This also we are not interested. So this has also been specified as 0 in the code. Then you would see xval. So this is number of cross validation. So what happens in the rpart function, some of the observations that are used for the building process, they are reserved for the cross validation purpose as well. However, we would not like to perform cross validation. Rather we would like to we would like to use the validation partition later on in another example that we will see. So at this point, because we are using all the observations here of the data, and we don't want to do cross validation. So cross validation is very similar to what we do using validation partition, but here in this case the observations from the training partition itself are going to be used to perform the validation exercise. So you can see after having understood some of these parameters, let's start again. Let's also discuss one more the parameter, which is there in the should be there in the previous page, the R part page. So let's go back. So params, this is optional parameters for the splitting function. So you can see what we have done is we have selected the splitting split argument. So split argument is actually this is the splitting this split argument. So what it does is splitting index can be Guinea or information. So in this case we have though by default it is Guinea only, but we have clearly specified Guinea so that we understand how we can use this function R part and specify the required splitting index. So in this case split is the argument within the params argument within that list. We can specify it as Guinea. So once we have understood the arguments and the function, let's execute this code. As you can see, the model has been built. Now let's look at the tree that we have constructed. So let's first set some of these parameters for graphics. Margin 0, outer margin 0, and then x PD value as NA. We would like to use the whole device region. More information on XPD you can keep on following the parameter functions and other related function to find out more about XPD argument here. So let's execute this. Now let's plot. So plot is we would like to plot the tree that we have just built. So this is the tree, and now we will have to add the information. This we can do using text command. So in the text command, using again the mod function and other arguments, we can fill this with more details. So this is our tree. So you can see annual income is the first predictor that has been selected, and the specific value that has been selected is 5.95. So the predictor value combination is annual income and the value of 5.95. So here if this value is less than 5.95, we will go to the left tree, and which will also be classified as non-owner, right? That is the terminal node here, and immediately we will get terminal node in the left branch. In the right branch, if the value is not less than 5.95, so we will go to the right subtree. And there again we will have to find out another another predictor value combination. So this comes out to be household area, this time 19.5, and then again if we two partitions, so right partition is actually terminal node, and then here in this part we have annual income less than 8.05, and further partitioning on the left side annual income 6.1, and the others are terminal node. So from this, if we compare to the hypothetical example that we had done, so here the first split is based on the annual income predictor and a specific value is 5.95. However, if we look at the splits that we have manually done, our hypothetical splits, right? So first split was at 18.8 using household area, right? In this particular graph you can see first split, this was the first split that we had created, right? This was at 18.8 using household area, but if we look at the split that is as per the tree using this card technique, annual income 5.95. so annual income 5.95. So let's look at in the original plot where this value is going to be. So annual income, and the value is going to be somewhere here 5.95. this is very close to 6, right? So this value the partition is going to be somewhere here in this fashion. So the partition will go up to this. So here you would see if the partition is created from here, right? So probably it will bisect these 2 points, right? Probably it will bisect these 2 points. So if we want to create a partition on this, so let's use the sum of AB line function that we had used earlier, the first split that we had created earlier. So that was at 18.8, right? So now let's use AB line to create the partition. So now this is going to be, we have to use v because this is going to be a vertical line, and this is going to be 5.95, and if we do this, we'll get this line. So now let's look at this. So this is the line. You can see this particular line. This is the first split as per the algorithm, R part algorithm, and you can see that this 5.95 predictor value combination for annual income, this and this particular observation is being split using this partition, and the left partition that we get, this is pure homogeneous. So and this other partition, of course, it is being dominated by the owner class, but it is going to have 4 observations belonging to non-owner and remaining 10 observations belonging to the owner. This particular left partition will have 6 observations belonging to the non-owner. So this is pure. So the probably this is the first partition which is creating, which is reducing impurity much more than what we had done. We had done this partitioning 18.8 using household area. Now this is the optimal combination, annual income 5.95. So if we were to compute the delta that decrease in impurity index, either Gini or entropy, we would see much more decrease in this particular case. So let's go back to our modeling. So once this is understood, now there is another way to create the tree diagram that we have created. So that the tree diagram that we had created using the plot function, this is the diagram. So if you like a more presentable tree diagram, much better than this, more nicer or pretty version of the tree diagram, then we have another we will have to use another package, that is rpart.plot. So we'll have to install this package. So let's load this library. So first we are required to install it because it's not already installed. So let's install this particular library. So once this package is installed, we will load it, and then we will have access to another function PRP, which can help us in plotting a more nicer version of the tree diagram or pretty version of the tree diagram. So let's load the library. Now this PRP is the function. So you can see first argument is of course the model, and then there are various other arguments that I am passing here. If you are interested in more details, you can always type PRP in the help section and find out more details about this particular function. So you can see plot and rpart model. So this is especially designed for the plotting, and you would see huge number of arguments that can be passed to this function. So too many arguments, so we would like to understand the few that we are going to use. So for example, the second argument that we have type, so that actually indicates the type of plot that we want to create. So in this case we have set type 1. So you would see what is type 1, label all nodes, not just leaves. So the default type would just label leaves, but we would like to label all nodes. That means decision nodes as well as terminal nodes or leaf nodes, not just the leaf node. So therefore we have changed the type to 1. Now next argument is extra. So extra, the value that we have given is 1. So let's look at what it means. So when the extra value is 1, then display the number of observations that fall in the node. So that split of observation to each of the classes, that is going to be displayed. That is the extra information that is going to be displayed. Had we opted for extra 0, then no such information would have been displayed. There are many other extra options, so that you can look at in your own time. Now the third argument is under, and that is specified as true. So let's look at this particular argument. Applies only if extra greater than 0. So that is the case. We have selected extra value 1, so that is greater than 0. So the under argument can be applied. So what it does, if it is true, so that this will put the text under the box. So the box that is going to be created, that we will see, right. So the box would be seen at each node, decision or terminal, and the text extra information that we talked about using the extra argument, that is going to be displayed under the box. Then we have varlen, another argument. So let's look at what this is going to do. So this is the argument. So length of variable names in text at this splits. So varlen is 0. So 0 means use full name. So there are other options also. So they will probably abbreviate the full name depending on the requirement. So because we have assigned the value as 0, so we don't want to abbreviate the names. So full names would be seen at this split. Similarly, other arguments are also there, so you can go through them on your own time. CEX, compress, margin, digits. So let's create this plot. So this is the plot that we get. So this is much nicer version of the tree diagram, or pretty version of the tree diagram. As you can see here, annual income 5.95. If it is less than that, and then the left branch. If it is not less than that, then the right branch. You can see the root node itself has been labeled as non-owner, even though there are equal number of observations belonging to owner or non-owner class. That is because there is no majority class, so they have just gone with the alphabetical ordering. So non-owner and owner, so N comes before O, so therefore non-owner has been used. So alphabetical ordering is used because there is no majority here. So the root node is also, as when we set type 1 and extra 1 that arguments that we understood from the help section. So because of this type 1, the labeling of decision nodes is also being performed here. So depending on the majority, that label is going to be displayed here. So you would see this is the terminal node that we have. So all 6 observations belong to this category. This is non-owner. Again you can see these split 6 and 0. This is again in the same order, non-owner first and then owner, right. So if we this particular discussion we have done before as well. When you when you define a particular variable as a factor variable in our environment, the labels of that factor variable, right, so they are going to be alphabetically ordered. So right, the same ordering scheme is again being used by this particular tree diagram. So 6 and 0, 6 number of non-owners on all observation belonging to the non-owner category, and that is the label also. Now we look at the right right subtree. So the second split would be performed, household area less than 19.5. So this is going to perform. You can see 4 and 10 is the split at this node. So 10 is the number of observation belonging to owner, and this also is the majority in this particular situation, and the owner labeling has been used. So if the household area where is less than 19.5 will go to the left side, otherwise will go to the right side, which also happens to be the terminal node, and that to owner. So in this fashion we can understand this particular tree diagram. So this is full grown tree. So because we had just 2 predictors, and we had also just 2 classes in our outcome variable. So this particular tree is quite small. However, if we are dealing with more than 6, 7, 8 predictors, and we are trying to build a full grown tree, this particular tree diagram is going to be much more messy, and many more decision nodes and terminal nodes are going to be displayed. So therefore the visualization or analysis, graphic visual analysis would also become more difficult in those tree diagrams. So let's go back. If we are interested in visualizing the tree diagram which is there after first split or second split or third split, that can also be done in R. So for that to be performed, first we need to understand the node numbering. So how node numbering happens in a tree diagram. So the same function that we have used PRP for plotting of the tree, there we have another argument NN. So this particular NN argument, as you can see here in the code, this is specified as true in this case. So therefore node numbering for all the nodes is going to be displayed, and we have also character expansion also for node numbering is done, so that it is not much larger than in comparison to the diagram. So let's create this tree diagram with node numbering, and let's zoom in. Now you would see all the nodes have been numbered here. So root node becomes the 1, then left this left terminal node 2, then 3. Then you would see suddenly after 2 and 3 we get to node number 6. So that is because in the tree diagram, if we want the unique node numbering, and even if a particular node is not present, it is assumed, so numbering is skipped for that particular node, but the numbering is done. So for example, 1 root node is 1, so it can have 2 childs, left child and right child. So left child is going to be number 2, if it is present it will be displayed as well. Right child, it is going to be number 3, if it is present, if it is going to be displayed. Then we again come back to the left part of the tree diagram, and again we look at the second node, that is the left child of root node. And in this case we see that there are no further partition, there are no further childs of this particular node, but had it been there, they would have been given the number of 4 and 5. So there would have been 2, so 4 and 5. So those numbers are not being used, but they are counted here, and the next node at the same label, that is right, third label, is going to get the next number, that is 6 here. So this fashion will give us the unique node numbering for all the nodes, and also will also get to know which node numbers are not part of the tree. So this gives us some flexibility in later on more processing, more computation that would be required later on, we'll see. So similarly 6 and then say at same level, so we'll keep on moving at the same level. So this is the 7th node. Then you would see suddenly from 7th we reach to 12th, because had this particular node number 2 had 2 childs, they again had 2 more 4 subchilds would have been there at this level. So 8, 9, 10 and 11, for those 4 subchilds would have been there, but they are not part of the tree. So numbering comes to 12. So in this fashion numbering can be performed. Now why we have done this kind of node numbering, and that to unique node numbering, even if a particular node is not part of the tree, we'll understand in few seconds. So first split, we create first split, that is in this case is annual income value 5.95. so that is the first split at root node that we perform. So if we just want to display the root node only, then the full grown tree that we have developed, that is represented by mod. So we can call snip or part function. So let's look at the function, this particular function, snip or part. Snip subtrees of an R part object. So using this particular function, we can snip the tree, we can remove some of the nodes in the full grown tree, and look at just the part that we are interested in. For example, if we are interested in the nodes that have been created after first split, that is root node and then the 2 child nodes, just 3 nodes if we are interested, and of course the corresponding terminal nodes. So then we will have to snip the remaining part. So how do we snip the remaining part? So let's again look at the plot. So this is the plot. So first split at root node 1, so we'll have two nodes here, 2 and 3. So the other nodes like 6, 7 and others, we would like to snip them off. We would like to remove these nodes. So this using a snip part function, we have to pass this full model for full grown tree, and then you can see we are passing on the unique node numbers of the nodes which we want to snip. So you can see 6 and 7 they are present, 12 and 13, right, and then 24 and 25 the last level, right. So we would like to get rid of these nodes, so this part would be removed off, and then we would be left with the part which is which we would actually see after first split. So let's perform this snipping. Now once this is done, we'll get another another model, another object of our part type, our part object. So we can plot this using PRP function. So now we would be able to visualize just the snipped part after first split, right. So now you can see root node and then the two child node and then the terminal nodes, right. So this is how we can see what is going to happen after first split. So root node we had 10-10 similar proportion. This was the predictor value combination, annual income 5.95, and then left child was the terminal node immediately. Then the second one, this one owner, again further partitioning. So second split is also in a way shown here, a non-owner and owner here, right. So in this fashion we can actually focus on the actually display the part that we are interested in. So first split and two childs we can see. So we'll continue this discussion in our next lecture. Thank you.